Alright, we want to show that polynomials in Z satisfy the divisor chain condition, or rather Z adjoint and indeterminate satisfies the divisor chain condition. I understand there's sort of a process behind this that I understand, but I'm not sure if I explain it super clearly. So I'm going to explain how it works. This might not be the most crystal clear or the most beautiful proof in the world, but it should get the point across. So suppose P1, P2, and so on, just some list. We don't know if it's finite or infinite yet, but we're going to prove it's finite. Zx are such that Pn plus 1 is a proper factor of Pn. No. Yes. Proper factor of Pn. Let for all n and n, let the degree of Pn be Dn. Then if, let's see here, so then if m is greater than or equal to n, then p, rather than, n is less than or equal to m, means that the degree of m, of pm, is less than or equal to the degree of pn, meaning that as you go up in index, the degree of the polynomials will either stay the same or decrease. For any Pn, I claim there are only finitely many indices, we'll say m, greater than or equal to n, such that dm is equal to dn. To prove this, note that if Pn plus Pn plus 1 times P prime equals Pn for some polynomial P prime, and if the degree of Pn plus 1 is the degree of Pn, then these imply that the degree of P prime equals 0. So P prime is a constant polynomial, but we know more, which is not, certainly it's not 0, because we don't consider 0 to be a proper divisor. And for it to be a proper divisor, it can't be a unit. And what are the units of these polynomials? Well, the polynomials which are plus and minus 1, because those are the units of z, and not 0, 1, or minus 1. Also, the constant P prime divides the greatest common divisor of the I'm going to call it the GCD of Pn. And what I mean by that is the greatest common divisor of all coefficients of the terms of Pn. And that's because if we have like an x to the n plus, or let's see here, a0 x, if we have a0 plus a1 x to the 1 plus all the way up to an x to the n, and P prime is just a constant value that divides all of these, then it must divide a0, it must divide a1, and it also, all the way up through, it must divide an. And so if it divides all of these, then it must divide the greatest common divisor of all of these. So let's see here. By prime factorization, this is of course in Z because we can do that in Z, and that's important here. GCD of Pn is equal to Q1 N1 all the way up to QK to the NK, where QI are primes. See here. And we have uniqueness of this factorization up to like units and stuff. You can put like -1 in one of these and stuff. It's essentially up to units. This is unique. And so then at most so at most let's see here. So let's see here. So Pn plus the sum from j equals 1 through n of nj, because nj's, these are the exponents of these primes, plus 1 cannot be a constant polynomial which divides, cannot be a constant polynomial which divides Pn. Or rather, if this is of course if Pn plus 1 all the way up through. Oh wait, no. No, what are the here. We got to be specific about these. So Pn prime is going to be dividing Pn. So implies the degree of Pn prime is this. So Pn prime, the constant Pn prime divides the GCD of Pn. So this thing, this divisor of Pn plus the sum plus 1 cannot be a constant polynomial which divides Pn if Pn plus 1 prime through Pn plus sum from j equals 1 to n and j prime are constant. And so this is what I mean by this being sloppy, in that like I'm not very clear, like there's kind of a lot going on here, but the basic point is that what this proves is Pn plus sum from j equals 1 to n and j plus, let's see here, plus 1 must, or rather the degree of this must be strictly less than dn plus sum j equals 1 to n of nj. Right? Because basically if Pn plus 1 prime through Pn plus the sum prime, if any of these are not constant, then they have to have a degree strictly greater than 1, in which case this inequality holds. However, if all of these are constant, then this last one cannot be a constant, because in this case you've gone through all of the possible divisors of the GCD of these polynomial coefficients, and so it must bring down the degree. And so that's really the crux of this argument. So hence, and of course I could go into more detail here, the sequence P1, P2 is, or rather it terminates. Because you eventually get to a point where you end up with because every time you divide by a polynomial, you either decrease, every time you go from like Pn to Pn plus 1, the polynomial either decreases in decreases in degree, or you decrease the greatest common divisor of the coefficients. And these things can only, even though every time you decrease the degree, you could end up with completely new constants, and so the GCD completely restarts. But it still has a finite ticker. You can only bring it down so many times before you have to bring down the degree. And so eventually what's going to happen is you're going to end up with some polynomial which cannot be factored, which is like an irreducible polynomial in the sense that it cannot be divided by a polynomial of degree greater than or equal to 1. And so at this point you have a polynomial whose only divisors are constants. And that will eventually run out because there's only so many factors of the greatest common divisor of all of the coefficients. And so eventually what you're going to be left with is you're going to be left with some polynomial that is completely irreducible in z adjoin x. Which means that not only is it not divisible by any other polynomial of degree greater than or equal to 1, it's not divisible by any constant either. And so I know it's a little hand wavy and it's a little ambiguous, but I hope that kind of gets across how this process works, and I hope that it's convincing that this process will end after a finite number of steps. And this proves that z adjoin x does satisfy the divisor chain condition. And so with that, we have completed this exercise.